done in RISC or any, we have done multiple instruction formats. In those instruction formats we are performing one operation per one instruction, but in these architectures we have multiple operations to be performed using one instruction. That is why these architectures are known as complex instruction set. And the multiple operations lead to many different kinds of instructions that access memory, in turn making instructions length variable and fetch, decode and execute, and thus hardware handles the complexity. CISC philosophy: use microcodes. CISC computers always use microcodes. Use a simplified microcode instruction set to control data path logic. That is, data path logic means the flow of data from the starting, taking data, processing that data and producing the output, or that is known as information. And that all flow of the data from starting to end is known as data path logic. This type of implementation is known as microprogrammed implementation. That is, microprogramming, that is that programming or those codes are implemented using the microcode instruction set to control the flow of data. Build rich instruction sets. Consequence of using a microprogrammed design is that designer could build more functionality into each instruction. Because this is a complex instruction set computer, as its name implies. In this we have I have already explained that why we use complex instructions, and in one instruction multiple operations. Build high level instruction sets. High level instruction set means the logic next step was to build instruction sets which map directly from high level languages. Means we have an programming language like C or C++. There is a rich logic's next step was to build instruction set which map directly from high level languages to low level language. Means highly featured intermediate language, that intermediate between a low level language and a high level language. That is mapping, or we can say interoperability between two languages. Characteristics of a CISC: registers to register to register, register to memory, and memory to register commands. In these CISC computer systems, we can perform the communication operations from one register to register communication. We can transfer or we can say we can send contents of one register to another register. Register to memory communication is possible, and vice versa. This memory to register communication is also possible, and these commands are executed using these registers and memories. It uses multiple addressing modes. Because we have a complex instruction set, means it means one instruction, multiple operations, so we need multiple addressing modes. Variable length instructions, where the length often varies according to the addressing mode. Length varies. The reason of varying the length is that the number of operations are not specified, not fixed in any instruction. In one instruction we can have one operation, or we can have multiple operations, and number of operations are not fixed. That is why the length of instruction is also not fixed, it is a variable. Instruction which requires multiple clock cycles to execute. Now we will compare the complex instruction set computers and reduced instruction set computers. First, in CISC, primary goal is to complete a task in a few lines of assembly language. It means to reduce the number of instructions, or to number of coding lines. And in RISC, primary goal is to speed up individual instructions. So the main goal of the reduced instruction set computer is to increase the speed of the system. CISC emphasis on hardware. It means it only hardware oriented. It use the hardware capabilities, and RISC emphasis on the software. CISC includes multi-clock cycles, and in RISC it use single clock cycles. and it is a complex instructions, as the CISC's name implies, that is a complex. It uses complex instructions. Instructions are complex because in one instructions we have multiple number of operations to be performed, and in reduced instructions only, because in these instructions only one operation per instruction. In this CISC we have memory to memory operations, and in RISC we have register to register operations, load and store intercooperated in the instructions. And in CISC also we use load and store are independent, but these are independent instructions. In CISC architectures, it is difficult to apply pipelining. We will also study what is pipelining in the next slides. And it is easy in RISC systems, it is easy to apply pipelining. Small code size, high cycle per seconds in CISC, and in RISC low cycles per second and large code size. Now we will study what is an instruction pipelining. Now we all know what is an instruction. Instruction is the command given to computer. Instruction, in instruction we take data, address and the operation to be performed. One instruction can be similar to manufacturing assembly line. It means an instructions can be the processing of the whole instruction is divided into 4 parts. The timing of the instruction performance is divided into these 4 parts. First cycle or first phase of the this processing is known as fetch an instruction. That is, it means fetching means taking instruction as input or taking command, that is fetching the instruction. And second is the decode the instruction, that is manipulating the code of that instruction to produce the executable form of that instruction. And third is execute the instruction, that is the main core part of this processing out of these 4 steps. In this third step, execution is done, that means operations are performed at the processor level. And the fourth is store results. The results produced by the execution phase are stored or produced as an output in the 4th stage. Each stage process simultaneously after initial latency. Each one execute one instruction per clock cycle. So we will study in this diagrammatical view pipeline stages. These are basically known as pipeline stages. Some processor uses 3, 4 or 5 stages. According to processors, multiple different processors use different architectures or different number of stages for one instruction. For example, in first A part, we have divided one instruction execution is in 3 parts. First is fetch instruction, second is decode instruction and select registers, and the last is execute instruction and store results. So in one clock cycle it will fetch an instruction, in second clock cycle it will decode an instruction, and in the next third clock cycle it will execute and store the result. So in the last clock cycle it will perform both the operations, execute the instruction and store the results. And in B part we have 4 stages in the instruction cycle. Fetch instruction, second is decode instruction and select registers, and third is execute instructions and store results. In this B part, the last stage that was in previous structure is divided into 2 parts. The execution instruction is in a different cycle, and in the next cycle it will perform the operation of storing the results. And in 5-stage pipelining, we have first is it fetch instructions, then it decode instructions, then in select registers. As we in 3 and 4 stage processors, there is a combined operation of decode instruction and select registers, but in this 5-stage processors we have first fetch instruction, and decode instruction and select registers are different operations, and these are performed in different clock cycles. And next is the execute instruction, and last is the storing results. Most commonly used pipelining is the 4-stage pipelining, that is fetch instruction, decode instruction, execute instruction and store results. This is the way of organizing pipelining. In the first half of this slide, what is it? Sequential processing of instructions. It means if we have a 4-stage instruction, then first 4 cycle will cover one instruction, that is A, task order given and time is also given, and in from 5th to 10th clock cycles will cover operation B, and in 11th to 8th, 9th to 12th will cover next, and so on. It means one instruction will complete its execution in number of phases, number of cycles in the corresponding to the number of stages in that instruction cycle is used. But in the pipelining we perform the operations. Pipelining, multiple processes are executed simultaneously. It means if we have different processes, like in this, fetch instructions need different having different requirements or resources, but decode instructions need different resources, and in execution and store are also different resource requirements having. In fetch we need input phase, in decode and execution we need processing phases, and in last we need output devices. So all the requirements of all these stages are different. That's why we can use pipelining. We can say all the processes can be executed simultaneously. So we will study instruction pipelines. It is to prepare the next instruction while the current instruction is still executing. A 3-stage RISC pipelining is explained in this diagram. First is 3 stages are: first is fetch instruction, second is decode and select registers, and third is execute the instructions and store the results. So in this diagram there are 3 instructions, that is 1, 2 and 3 stages, 3 stages, 1, 2 and 3. There are clock cycles 1 to 7. Horizontally displayed numbering is the clock cycles, and vertical displays 1, 2, 3 is the stages of the pipeline. So here I1, I2 and I3 up to I7 are instructions. That is, I1 is first instruction, I2 is the second instruction, I3 is the fourth instruction, third and fourth and up to 7th instruction. In this cycle, in this tabular diagram, we can display the execution of the instruction. So in first clock cycle, instruction I is submitted and it is fetched. First stage of the first instruction is covered, and then in the second clock cycle the second instruction is fetched and the first instruction is decoded and registers are selected. And in the third stage, third instructions is fetched, and then second instructions is decoded, and the first instructions last stage is covered, that is I1. So we can say in first cycle second and third stages sources are available free, but in next these are busy, and up to end we can consider that per clock cycle we can execute, or this pipelining execute one instruction. So this displays the timing of the instruction 1, for example, from 1 to 6 clock cycles. First instruction starting from 1, it covered in the 6th clock cycle, and second instruction starting from the 2nd clock cycle, and it covered in the 7th clock cycle simultaneously, and up to last instruction it is processing is simultaneous processing. That's why it is known as a pipelining operations. Sorry.